So today we're gonna work on this optimization problems on this worksheet. I think you probably have it from the course coordinator Clifford, and we have 7 questions. I will see if I can go over all of them. Probably not because they're very lengthy. Okay, I think somebody's mic still on, and let's mute it. Okay, so start with the first question here. Find the point on the line y equal to 2x plus 3 that is closest to the origin. First question here. So firstly, we need to grab this line. We know how to do it. Right, the line is here. It has the y-intercept here, and is ascending like this. Right, and from the graph, you can see that the point that is closest to the origin is around here, around this place x, y. Right, so we can approximate this from the picture. And now, how do we find it? Is we're gonna go from the distance formula because we're looking for the distance, right? So the distance is equal to this one is the difference of the x coordinate, right? The difference of the y coordinates, and then you take the square, and then add up the sum, and then take the square root. That is the formula from the textbook. And since we are looking for the point, the distance from the point x, y to this origin, right? So we're gonna take x2 equal to the coordinate of this point, which is x, and then your x1 is gonna be the x coordinate of the origin, which is 0, right? And then you plus this y minus 0 square, just plug into the formula. So you end up with x squared plus y squared. That is the distance. It's written like that. And because we also know that the relation between y and x, y is equal to 2x plus 3, so I can replace this y with this expression. I plug in y here. So I now have the distance expressed in terms of only one variable, that is x, that is here. Okay. And now I open a bracket to do some simplification. So this is the perfect square formula, right? It becomes 4x squared plus 12x plus 9. That's just this formula. A plus b squared equal to a squared plus 2ab plus b squared. And now I combine those similar terms, and I have 5x squared plus 12x plus 9, okay, here. Okay, and well, remember our goal is to minimize this thing, so we want the d distance to be as small as possible, right? But we have a square root here, so what do? Well, so the thing is here. Notice that the value of x that minimizes d is the same that minimizes d squared, right? So that means the smaller the d squared is, the smaller d is. So they're the same thing, right? So to minimize the distance d is the same as minimizing d squared. So that's why we have this expression here. Denote the d squared by capital D. So our next goal is to just minimize the capital D, the d squared. So now I have my capital D, just the thing inside the square root, written like this, 5x squared plus 12x plus 9. And to minimize this, we need to find the absolute mean of this function in its domain, right? In its domain. So we're gonna take the derivative, right? Take the derivative with respect to x. So this becomes tan x plus 2, right? And then we let the derivative equal to 0, and then solve it. We have x equal to 12 divided by 10, negative, right? Which simplifies to x equal to 6 over 5. So we have this 6 equal x equal to negative 6 over 5. It's our critical number, and it's the only critical number we have, right? And now we want to determine what kind of point this is. Is it the local max or local min? We don't know, right, for this critical number. So we're going to take the second derivative, which is here, right, to test what kind of point this is. And the second derivative tells us that this is greater than 0. So this critical number is a local minimum. So local minimum here by the second derivative test. By second derivative test, local minimum. And here just to state that the function is continuous, right? And this is the only critical number, and this so this local minimum, it's also the absolute minimum, right? So we know that we have found this absolute minimum. That is just the point where x is equal to 6 over 5, negative 6 over 5. So after we have located this absolute minimum, we just need to compute the y-coordinate of this, right? Y-coordinate, how do we get that? We plug this x equal to 6 over 5 back into the line expression here, right? Back in here. So we have now 2 times this plus 3, which is 3 over 5. So now we have the also have the y-coordinate of that point, that desired point, right? And so the answer is negative 6 over 5, comma 3 over 5, which is approximately here. You can see from the picture, right? Negative 6 over 5, negative positive 3 over 5. This is negative 6 over 5, 3 over 5. Here, this point. So that is our question 1. I think very simple and straightforward. The only thing that we need to make use of is the distance formula. That is the only thing apart from the derivative stuff. Okay. So now I think we can move on to the second question. So now the second question, if this amount of material is available to make a box with a square base and an open top, then find the largest possible volume of the box. Okay, so basically you have limited amount of materials that you can use. It's not as much as you want, but you want to make the largest out of it. Right? What do you do? So that depends on how you design the box. So firstly, we want the largest volume. Right? Volume. So we must understand the formula of the volume of a box. Right? So we have, because we have a square base, so we can let the side of the base equal to x, right? They're both x here because it's square. And then the volume is equal to the height times the area of the base. Right? So this one here is area of the base, x squared. And this y here is the height. Right? This y here is. So now we can express the volume in terms of xy here. That is x squared times y. Okay. But also we're gonna look at the surface area, because that is the amount of material we have. Right? We cannot exceed this amount of material. So we're gonna figure out the surface area in terms of x and y. So that includes 4 sides here, 1, 2, 3, 4. That's the front side, right? This 2, the second side, 3 and 4, 4 sides here. And also the bottom, right? That's the fifth one, the bottom. We don't have the top. So that means we're gonna find the area of each side. That is x times y here, x times y. That is area of each side. And then we have 4 of them in total. So this is area of 4 sides. This guy here. The total area of 4 sides. And then of course this x squared is gonna be the area of the base, and because it doesn't have the top, so that's all for the surface area, right? And the total surface area must be 1200. That's what we have. We can't exceed this, right? So that is the condition. And now we're gonna use this relation to establish a relation between y and x. Namely, we want to express y in terms of x, so that we can plug this back into the previous expression, so that the volume can be written in terms of a single variable x, right? So what we do is to, of course, move x to the other side, move this to the other side. This one goes to the other side here, right? So this 4xy is equal to this 1200 minus x squared, and then you're gonna divide both by 4x. So divided by 4x here, 4x goes to the bottom. Now we have the y expressed in terms of only x. And after this, we're gonna plug this expression y back into the previous expression, so that we have the volume written in terms of one variable. That is, just replace this y. That's y with this expression, right? So now we have this x cancel with one of the x's here, right? So this x get distributed into both terms. This x multiply with this 1200 and this x squared, right? So it becomes 1200x minus x cubed divided by 4. So that is the expression of the volume in terms of only one variable, right? And then our goal is to maximize this volume instead of minimize it, right? Instead of like doing that in the first question. So maximize this thing, we're gonna take a look at absolute max, right? Absolute max. So we go back to the previous thing, that is to take the derivative of this function and work on the critical numbers. So take derivative, right? That is equal to this thing, 1200 minus 3x squared. And then we're going to let derivative equal to 0 to find out critical numbers, right? And now we multiply both sides by 1 over 2 by this 4. So this 4 is gone, right? So we have this thing equal to 0 by multiplying both sides by 4. And then we're gonna also divide both sides by 3. Both sides divided by 3. So this 1200 becomes now 400. And then this 3x squared becomes x squared. Right? And then we kind of do the factorization for this thing, the difference of square formula. This is a squared minus b squared equal to a plus b, a minus b. This 400 here can be thought of as 20 squared. This one is 20 squared. So now we have the factorization here, x plus 20, x minus 20 equals 0. Right? So the bracket, the product equals 0 is equivalent to either of the factors equal to 0. So we have x equal to negative 20 or positive 20. And because x presents the length of the base of the box, so it can be negative. We can't have a negative length in reality. So we will drop this negative solution, right? So we will not consider x equal to negative 20. So we only take this guy here. That is the only critical number we have. And now we're gonna look at the range of x, that is the domain of this function we have to mention. Right? Of course, the mean value of x can be 0, right? Is as small as 0. And the max value of x is when y equal to 0. So that you let y equal to 0, and then you solve x equal to this. If you think that is a little bit confusing, you can think of it like going back to the original function, right? You can, we must have y greater than the y greater than 0. So going back to here, y must be greater than 0. So we must have this thing, right, greater than 0. This 1 over 1200 minus x squared greater than 0. And then you can solve this inequality. That gives you x is less than 20 square root of 3. And it's basically the greater the x is, the smaller the y is. And the smaller the greater the y is, the smaller the x is. Okay? So we have now the range of x here by solving this. That is from 0 to 20 square root of 3. And after we have this, we're gonna take a look at our critical number, right? That sits inside this interval. 20 is inside this interval. So by number line, it can be presented like that. Have 0 to 20 square root of 3, and then the 20 sits between it, right? And this is gonna be the local max or local min, we don't know yet, right? So we're gonna take the second derivative like before to test what kind of point this is. The second derivative tells us that this is less than 0, right? So this must be a local max, right? So 20 is here, local max. That means the function was first increasing, then decreasing. Right? This can also be attested by this the first derivative test. That's up to you. But as long as we know that this is a local max, we're gonna proceed, right? Local max here. Local max in this interval, right, is also gonna be our absolute max, right? Just like the previous question, because this is the only critical number, and we're gonna proceed here just to plug in 20 into our volume expression. So now we have this 1200 times 20 minus 20 cubed, which finally comes to 4,000. So now we have that our largest possible volume of the box is 4,000 cubic centimeter. So that is question 2, very similar to our question 1, right? We have only one critical number here. And apart from doing the derivative, the only thing here is to figure out how to write this surface area and also the formula for the volume here. And apart from that, there's nothing much different than doing the derivative stuff. Okay, so that is our second question, and now we can move on to the next question, the third question. The third question here: find the dimension of the rectangle of the largest area that can be inscribed in a circle of radius r. Okay, go to the third question here. So basically you have a circle of radius r, right? And you want to inscribe a rectangle inside it so that the rectangle is as large as possible. So there are many ways of doing that. You can make the rectangle very skinny, right? So it sits inside this circle, but absolutely it's not going to be the greatest. It's not going to be the greatest rectangle, right? So you might want to make the rectangle like a less skinny and more flat, like that, right? So there are many ways of doing that, and which way will give you the most out of it, we don't know. So that we're going to figure it out. So now our rectangle is here, right? And then we're going to denote the length of this rectangle by x, and the height of this rectangle by y. And of course, the radius of this circle is r. So that is from the center of this rectangle to the edge of this circle. That is equal to r. Now we write out the expression of the rectangle. That is the length times the height. So the area is equal to x times y. Simple like that, right? And because this is in terms of two variables, we will eventually need to eliminate one of the variables. So we're going to find a relation between the variable x and variable y. That's why we want to make use of the rectangle here. The rectangle here. There's a right rectangle in this upper corner of this rectangle. A triangle, sorry, a right triangle here. And so now this is r, right? And then the height is half of the height of the rectangle. That is 1 over 2y. And the side here is going to be half of the length of the rectangle. That is 1 over 2x. So that is what this triangle looks like here, a right triangle. And we know we have the Pythagoras Theorem for right triangle. So the hypotenuse square, r square, is equal to the square of this side plus the square of that side. So now we open the bracket, and then we have r square equal to 1 over 4x squared plus 1 over 4y squared. And then we're going to multiply both sides by 4, so that 4r squared is equal to x squared plus y squared. And now we're going to move the x to the other side so that we can solve for y. Right? So move x to the other side. We have 4r squared minus x squared here, and then y squared here. And then we take the square root. Now we have y expressed in terms of only one variable x. That is plus and minus the square root of that. You might be wondering why do we also have r here? Is r a variable? Well, r is a constant, right? It's the radius of this circle, which is unknown, but is a constant. It's not change when x and y changes. So we're gonna view this as a constant, just like number 1, 2, 3, 4, just like that. And now for the same reason, since y represents the length, right, so it can't be negative, so we will drop the negative solution and only consider the positive solution. So now y is equal to this one. And after now we have this y, we're gonna have this plug in to our previous expression area, so that we can have the area written in terms of only one variable. So now this a is equal to xy, right, which is written in this form. This y is replaced by this square root thing here. And then we let x go into the square root, so it becomes x squared, right? So it becomes x squared. Now we have 4r squared x squared minus x to the 4. It was originally x to the 2, but it multiplied with the x squared, so it becomes x to the 4. So it looks very similar, right? We have this square root thing, which is difficult to compute. So to maximize this a is the same as maximizing a squared. So we will take a squared as our capital A, and our goal is to just maximize the inside function in the square root. Just like how we did the first question, we take d squared to be capital D to maximize this inside function. Okay, now the setup here is done. Now we just need to turn to the derivative stuff to figure out critical numbers and local max, local min, and all sort of those things. So we're gonna take the derivative of this function, function a, right? So we're gonna have 8r squared x minus 4x to the 3. And remember here, r here is treated like a constant, right? So you're taking the derivative with respect to x. You're going to view this r squared as a constant, just multiply it in the front. You're not taking the derivative of the r. So that's very important to pay attention to. We're taking the derivative with respect to x here. So only x here is the variable. And now we're going to do factorization, just like we did before. Factor out this x, and then we have this bracket 8r squared minus 4x squared equal to 0. And product equal to 0 is equivalent to either of the factors equal to 0. So we either have x equal to 0 or this equal to 0. This equal to 0 gives us that 4x squared is equal to 8r squared, and then we have both sides divided by 4, right? This 4 is gone, and this becomes 2. And then we take the square root, so that x is equal to plus or minus r times square root of 2. And for the same reason, we will drop the negative solution, because in reality the length cannot be negative. So we only consider this positive solution, x equal to r times square root of 2. Right? So this is our critical number. This is critical number here. Okay, so after we have the critical number, also this is our critical number, right? X equal to 0. So after we have the critical number, we're gonna consider the function on the interval x from 0 to 2 pi. The reason why x can be 0 is obvious, right? That's the smallest value x can be. But why it can be 2r here? That is because when you look back to the this rectangle, you see that the length of this side x, right, can be at most as long as the diameter here. It cannot exceed the diameter. So the maximum value that x can get is 2 times r, which is the diameter here. Okay, so that is why we have x in the range of from 0 to 2r. Okay, so inside this interval, we're gonna test the function value at each single point to determine which value is greatest. And we also using the closed interval method, right? The closed interval methods tells us that the absolute max, absolute min exist, right, is either at the endpoints or at the critical numbers. So we're going to plug in critical numbers here and these two endpoints to the original function, the expression a, to test at which point we have the greatest value. Right? Keep in mind that our function a is this one. This is our function a. Gonna plug in this to test. This a is here. So plug in 0, right? You have a equal to 0, that's obvious. And then you plug in r square root of 2. Go through a little bit computation. That tells you the area is 4 times r to the 4. And you also plug in 2r, right? That also gives you 0. So it's clear that the absolute max occurs at a place x equal to r times square root of 2. And the maximum area that we can have is 4 times r to the 4. Okay. So after we have this, we're gonna go back to the dimension of the rectangle to figure out what y value is. Right? When x is equal to square root of 2, right? We plug this back into the expression y to figure out the height. And then we have the height is also equal to r times square root of 2. So it just means that if you want to get the most out of it, the rectangle you draw here, it must be a square. Right? So it must be like that. That's how you get the most out of it. And it can also be easily be visualized that this when this becomes a square, the area is the largest. Like that, approximately. So this is r square root of 2. The height here is also r square root of 2. So that is the greatest rectangle we can get inside a circle. Okay, so dimension of this, r square of 2 times r square of 2, right, square, with the length this. So that is our question 3. It's also very similar to question 1, I think. Okay, seems pretty good. And we now can move on to the next, question 4. Question 4, we have a cylinder that is inscribed inside a sphere of radius r. So that is also similar to question 3, right? We want to find the largest value, possible volume of such a cylinder. So let's see how do we do it. Okay, question is here. Right? So this is a sphere with a radius r, just like a ball, basketball. And then this cylinder is going to be inscribed inside this sphere. Right? We want to get the largest volume. So firstly, we're going to write out the volume formula. The volume formula is equal to pi r squared times h, where h presents the height here, right? And the r here is the radius of the cylinder. So don't mix that up with the lowercase r. Lowercase r means the radius of the sphere, and capital R here means the radius of the cylinder. And we're gonna have the base, the area of the base of the cylinder here, multiplied by the height, so that we have the volume of the cylinder. Right? So this pi r squared means the area of the base of the cylinder, which is here. the orange area here, times the height. So now, after we have this volume written in this form, we have two variables, right? One variable is the r square. This r can change, so you can make the cylinder more skinny, so that r could be smaller, right? But in the same time, it will be taller, so h will be larger. Or you can make the cylinder like more flat, so that you have greater radius, but in the same time, it will be very short, so the height will be small. So both the variable r and h can change depending on your design, depending on your choice. So same as before, when we have two variables, we will need to eliminate one of them, right? So we're gonna find the relation between the variable y and variable r and variable h. So we start here by looking at this triangle, this right triangle right here. That is this guy here, this triangle. So now we have the height of this triangle equal to half of the height of the cylinder, that is 1/2h, right? And then the radius of the cylinder is here, capital of R, and then the hypotenuse of this triangle is lowercase r, that is the radius of the sphere, right? And we're gonna use obviously the Pythagoras Theorem, so that hypotenuse square is equal to the square of this side times plus the square of that side. So we have r square equal to this capital R square plus h divided by 2 square, and then open the bracket, so this becomes h squared divided by 4. And now we're gonna solve for r square, so we're gonna move this to the other side. So now this r square can be written as lowercase r square minus h square. And now we're gonna substitute this r square back into our volume expression. So this is gonna substitute in here, right? So this guy is gonna be replaced by the lowercase r expression here. So now my volume is written as pi times this guy. It was originally r squared, but now it's been replaced with this expression times h, right? You might be wondering, we replace this capital R of a lowercase r, so we still have two variables, right? But that is not the case. Remember, capital R's here can change depending on your design, but the lowercase r here is a constant, is a fixed number. That is the radius of the sphere. It was originally given, right? It does not change. So by substituting this in the r square, we can we manage to eliminate one of the variable r. We only have one variable, the other variable h here. So that is why did we do that? Okay, so remember this r here is a constant, right? Constant. Okay, we will just treat it like 1, 2, 3, 4, like numbers. And now we're gonna open the bracket, simplify this expression. We have pi r squared h minus pi over 4 h to the 3. Okay, this is gonna be our function, the volume function. And our next step is obviously to take the derivative, right? So take a derivative with respect to h. And also remember, r here, this lowercase r is a constant, right? So we're not taking derivative of this, just a scalar, this pi r squared, just like a number 1, 2, 3. So the derivative of this term is gonna be just pi r squared. And the derivative of the other term, this guy, this 3 goes down, right? It's 3 here. and the power becomes, this minus 1 becomes 2. Right? So this is just the power rule, right? And then we let the derivative equal to 0 to find out critical numbers, okay? And then firstly, we're gonna, have two sides divided by pi, so that these two pi's are gone, right? No pi anymore. And then we have r squared equal to minus 3 over 4h squared, right? And then move this to the other side. And then multiply both sides by the reciprocal of this, 3 over 4. So we have h squared equal to 4 over 3r squared, right? We're solving for h in terms of r. And also remember, again, r is a constant. So now the variable h is solved, right, in terms of this. And we have two solutions. And of course, we need to drop the negative solution. In the reality, we don't have negative height. So now we have this critical number. And we were wondering what kind of point this is. It could be local max, local min. We don't really know. So we take the second derivative again to verify this. Take the second derivative, right, from here, right? When we take the second derivative, this term is gone because it's a constant term, right? So we are left with taking the derivative of this, and that is 6 pi h divided by 4. Okay, this is a negative value, a negative number. So because it's negative, so we have local max here. Here is a typo, should be less than 0. Okay. So we have a local max here. Okay, local max. And next, we're gonna consider the range of h, because our function v is written in terms of h, right? So h can be as small as 0. That's when the cylinder is entirely flat. So the height is equal to 0. That is easy to imagine. But what is the greatest value, greatest possible value of h? We go back to this cylinder here, right? When you make the cylinder very, very skinny, it could be like that. So you can see the height here is very close to the diameter of this sphere. That is 2r. And in the extreme situation, we can think of like the height being 2r. So that's here. So that is why the range of h is from 0 to 2r. When it's equal to 0, you have the entirely flat cylinder. When it's equal to 2r, you have a very, very skinny, tall cylinder. Okay, so that is the domain of this function, h. And our critical number, that is h equal to this 2 over 3, 2 divided by square root of 3r, sits inside this interval, okay? And because it's a local max, right, it's the only critical number, so it's also gonna be our absolute max. So we can just plug in this to compute this. If you don't want to explain why this local max is also the absolute max, you can go by the extreme value theorem just to plug in the endpoint, right? 2 endpoints here into the function, and also plug in the critical number into the function and see which one will give you the greatest value. That also do the job, right? And after plugging in, when you plug in 0 and r to r, you have 0 here as the volume, and that is also easy to imagine. When the cylinder is entirely flat, the volume is equal to 0. And when the cylinder is entirely skinny, you also get a needle, 0 volume here. And then when this h is at this value, you get the most out of it. That is equal to this value. Okay, so that is our local max, also absolute max. So now that is the largest possible volume of such a cylinder we can get. So I think that should be very straightforward, very similar to the previous questions, right? In question 3 and question 4, both questions, we consider the extreme value theorem, find out the critical numbers, and then we are dealing with a closed interval, right? And then we plug in the endpoints and the critical number to see what kind of thing we get here. Okay, so that should be very clear. That is our question 4. Any questions so far? So if no questions, I will move on to question 5. Question 5, that is a long question, so let us read this question. That is from the exam, winter 2014. Rectangle storage tank is to have a square base, an open top. Okay, just like the box here in second question, we can imagine, right? Open top box, and must hold this amount of water, 64 cubic meters, and the material can be used for the bottom cost $4 per square meter, and the material for the base costs 16 per square meter. What dimensions for the tank will cost the least amount of money? So the model of this question is the same as question 2. You have an open tops box, but in question 2, the amount of material you can use is limited, is fixed. You want to get the most volume out of it. What is different in question 5 here, instead of having a limited amount of materials, you have infinite amount of material. You can have as much material as you want, but the cost here, it will be increased if you use more material. But the volume here is fixed, right? It has to have this volume. That is different from the question 2. Question 2, the volume, you want to get the largest volume. So instead of having a fixed surface area, now you have fixed volume, and you want to get the surface area kind of as small as possible. So it is the other way around, very similar to question 2. Just think about question 2 and just make a slight modification. We should be able to do question 5. Okay, now go to question 5. Question 5 here. Now it has a square base, just like question 2, right? So the box is like that. And then we're gonna denote the height by y. So the volume is x squared times y, which is equal to 64, right? But that is not our target function, because volume has been fixed, right? So it cannot change anymore. What we want to change is the surface area. So now we have x squared times y equal to 64, and then we can express y in terms of x. Just divide both sides by x squared, so y is equal to 64 divided by x squared. So that is the relation between x and y. Now what we want to really figure out is the cost of the box. So the cost including two parts. One part is the cost of the total 4 sides here, right? And the other part is the cost of the base, because material for constructing these two parts are different. They cost differently. So we're gonna figure out the cost respectively and then add them up. So the area of the base is x squared, that is very simple, and area of the 4 sides is 4 times xy. For the base, it costs you $4, right? That's the bottom. This is $4. But the bottom is going to cost you more. That's going to cost you $16, right? So we're going to multiply the area of the base by the cost of per square meter to obtain the cost of the base. So this thing here is the cost of the base. And the other one, right, that is 16 multiplied with the area of the total 4 sides. That's going to give you the cost of the 4 sides. Okay, and then we add up the cost. That's going to be our total cost C. And then we simplify it. 4x squared plus 64xy, right? We have 2 variables, and then just routine to eliminate one of the variables, right? We have the relation here. We're gonna plug this back into the expression here to replace this y. So now this y is gone, right? It's written in this x 64 divided by x squared, and then we cancel this x with the one of the x's in the denominator, and this function simplifies to this. So this is going to be our target function. We want this cost to be as small as possible. We don't want to spend non-necessary money. So we're going to take the derivative, okay? Take this derivative equal to 8x minus this divided by x squared, just by the Pell rule straight, and let the derivative equal to 0, okay? So this one is equal to 0. And then 64 squared, it can be written as 8 squared times 8 squared, because 8 times 8 is 64. And then we're going to get rid of one of the 8 here. So this 8 is gone, and this 8 is gone, right? So we're left with 3 8s multiplying together in here, right? Just a little bit algebra. So that gives us x minus a to the 3 divided by x squared equals 0. And we're going to multiply this by x squared, both sides by x squared. So you have x3 minus 8 to the 3, because this x squared cancel with this x squared. And that is very simple to figure out, right? That is the difference of cubes formula. A cubed minus b cubed equal to a minus b, a squared plus ab plus b squared, okay, which is applied here. So this factored as x minus 8 times this thing, okay. So this equal to 0 means either of the factors is 0. So it could be like this is equal to 0, or this expression equal to 0. But the point is that this expression can't be 0. It can't be 0. Because when we look at this discriminant, right, compute this b squared minus 4ac, discriminant is less than 0, means this equation has no solution. No solution means it can't be 0, right? This equality can't hold. So our only option for this expression to be 0 is when x is equal to 8, right? So that is the only possibility that will make the derivative equal to 0, right? So that is our only critical number here, only critical number. And then we're gonna, take the second derivative, right, from the first derivative, to figure out what kind of point this critical number is. Second derivative greater than 0, so it's a local main, right? And local main, we're gonna take a look at our function again, right? Our function, this is in terms of x, right? So x can be very small. You can make a very tall, skinny box, right? That's up to you. But in order to hold that amount of water, this is going to be very, very tall. So it's going to consume your material. So it's going to be very expensive in that case, right? And in another case, this x could be very large. So you can make a very flat box and very short box, right? That's not going to hold that much amount of water, so it's going to be very expensive in this way. So you can imagine x can be as small as 0 and it can be as large as infinity, right? There's no maximum bound, upper bound for the x here. So that tells you what the domain of this function is. So the domain of this function is going to be from 0 to positive infinity, okay? And then because x equal to 8 is the only critical number here, and then it's a local main, right? So this local main here is going to also be your absolute main. Okay, so this tells you that. And because it's absolute main, we can just plug in, right? Y equal to this, which we got from the beginning. And then we have y equal to 1. X equal to 8, y equal to 1. That will give you the dimension of the box, right? The box is going to be like a little bit flat, like that. Have the height equal to 1, and the length of the base is going to be equal to 8. And that can hold 64 cubic meters of water with the lowest price. Okay, lowest priced. So that is very similar also to those previous questions, right? How do we determine the domain of the function? We're gonna, go back to reality and see how we can construct this box. In the previous question, how we can construct the cylinder, right? It can be very skinny or very flat, and that gives us the domain. And in this question, the same thing is true. And then the same point that we are constantly using is that we have only one critical number inside the interval. So that is, if that is local max, that will be absolute max. If that's local min, that will be absolute min. Okay, so that is our question 5. I think it's also very simple. Any questions? I think we're in good shape, so we can move on to the next. This is the exam question from 2014 in the fall. Rectangle 10 meters long and 5 meters tall is to be cut perpendicularly to the base, and the result is two small rectangles, R1 and R2. So where could the cut be made such that the product of the area R1 and R2 is as large as possible? Where is it? 6 is here. Okay, so now you have this given rectangle, have the length equal to 10, and the height it's 5, right? And then you're gonna cut this perpendicularly. There are many ways of cutting it, right? You can cut it here, right? You can cut it here, right? You can cut it here. It's up to you. But our point is to consider the area of these two small rectangles and their product, right? We want their product of area to be as large as possible. So we're going to write out their product first. Firstly, write out the area of each small rectangle. So we're going to locate a cut here. Let's denote, we cut it at this point, which is x meters away from the left end. So the length here is equal to x, this length. Okay. So now we know the rest of the length here is 10 minus x because the total length is 10. Okay. So now we can express the length of the rectangle R1 and rectangle R2. Now we use the length to multiply the height to figure out the area of R1, that is 5 times x, and also R2, that is 10 minus x times 5. Okay, so that is the area of each of these rectangles respectively. So what do is we're gonna multiply these two areas, okay, these two areas here, and then we have 5x multiplied with 10 minus x times 5, right, which will be our target function a. Okay, in terms of only one variable x, that is very good. We don't have to eliminate other variables, so only one variable involved here. And then we're gonna simplify it. Okay, that comes to 250x minus 25x squared. And then same routine, let derivative equal to 0, and then we move this to the other side, right? So that 50x is equal to 250, and then both sides divided by 50, x is equal to 5, and that is our critical number. When derivative equal to 0. After we have the critical number, we're going to consider, okay, domain of this function. Okay, so that goes back to the construction of the two rectangles here, the cut, right? So we can cut it here, cut it there, right? So the smallest value of x can be 0 once you cut it at the very left end. The distance is going to be 0, so x can be as small as 0. And you can cut it on the other side here, very close to the right end. So that is when x is very close to 10, right? So x can be as large as 10. So now we know the domain of this function is from 0 to 10. Okay, after knowing the domain, and we know this critical number, we're gonna see what kind of critical number this is. So the second derivative put in practice here, and then second derivative of that, right? Take this again, negative 50 less than 0. So this is local max, right? The only critical number that is local max in this closed interval, that's also gonna be our absolute max. Okay, so both local max and absolute max. And because it's absolute max, now we can just plug in x equal to 5 into the area function, the product of area, right? So you can see that now to get the largest product, the cut has to be halfway along the rectangle. So you have to, you have to cut it in half like that. So the product is the greatest. And you can also imagine once you cut it like very close to this left side, since one of the rectangle is very small, right? And the product's not gonna be very large, right? And also the same thing is here. If you cut it very close to the right end, right? One of the rectangle is large, but the other is very small. So the product is gonna be also small. So only when you cut it in the middle, you get the most out of it. That is also easy to imagine, right? Okay, so that is our question 6. Very simple. We have the last question left. Let's see if we can get through it. Question 7. 2016. An open top box with a square base have the volume 4 meters, 4 cubic meters. Find the dimension of the box so that it uses least amount of material. So this question is even more simple than question 5, right? Again, you have an open top box with a square base, and the volume is fixed. In question 5, we need to figure out the cost of both parts and then add them up. That's going to be our cost function. But here, we only need to figure out the least amount of material that is used. So that is just the surface area being smallest, the least amount of surface area. So you can imagine this. Question 2, question 5, question 7, they're all the same. Okay, so now work it out. We have open top, square base, so the picture is exactly the same as the previous 2 questions. Formula: volume is equal to area of the base times the height, right? Volume is fixed, it has to be 4. And what can be changed is the surface area. So surface area has 2 parts because it's open top, so this is the bottom, and this is 4 sides. And then we add them up. Here's the total surface area we have, right? Just like before. And now we want to eliminate the variable y. So we're gonna use this one to express y, as here, right? You have both sides divided by x squared. So y here is equal to 4 divided by x squared. And then gonna plug in this in here. So that y is replaced. Plug into here. And there's y here. So now you have this 2 x's cancel, right? The function a is equal to x squared plus 16 divided by x. And the same routine, take derivative and let derivative equal to 0, right? And then you're gonna solve for x, so multiply both sides by x squared. This by x squared here, this by x squared. So this x squared times 2x becomes 3x squared, 2x to the 3. And this x squared cancel with this x squared, so 16 is here, right? And then you have both sides divided by 2, so this 2 is gone. 16 here becomes 8, okay? And then solve it, x is equal to 2, right? X equal to 2, right? This is a critical number. And we want to figure out what kind of critical number it is, right? So let's take the second derivative from here. Let me denote the first derivative. dA divided by dx was equal to 2x minus 16 divided by x squared. And then we're going to take the derivative of this. That's second derivative equal to 2 plus this over 3. That is a positive thing, right? Positive thing means local main. Okay, we have local main. After we have this local main, we're gonna take a look at the domain of this function. Okay, domain of this function. So that goes back to how we can construct this box. Again, this box can be very skinny and tall, so that the base, the length of the base is very small, right? As small as 0. Okay, so you see here. So in that case, x is very small, right? It holds this 4 cubic meters of water. Or it can be very flat and short. So x can be as large as possible, right? So it can be infinity. So that tells us the domain of this function is 0 to infinity. And whether you write closed interval or open interval here does not really matter, right? Because we're not going to take a 0 anyway, because that is 0, zero volume. That could not happen. So the main point here is to figure out x can be as small as 0 and it can be as large as infinity. And this critical number sits inside this interval and it's the only critical number, local mean. So it means it's also the absolute mean, right? We use this fact many times, right? Only one critical number. So local mean implies absolute mean. And because of that, we have the absolute mean, that is the least amount of surface area we can have. So we plug in, right? Plug in 2 into the expression y to figure out what y is. So x equal to 2, y equal to 1, the dimension of this box is obtained, right? 2 by 2 by 1. So that is the best box we can build to contain 4 cubic meters of water with the lowest price. Okay, so that's all, right? Very simple, and I believe we are ready to handle the exam questions, right? After we go over this worksheet. Okay, any questions?